let's, first day really of review. Let's look at the mini mock exam first thing. So go ahead and let's look at problem number 1. All right, so the first thing is, I'm going to give a lot of analogies and things like that to help you guys remember these things, okay? So when you see the limit as h approaches 0, okay, there's really only one situation where you see this. Okay, so I want you to imagine a little bell like that's at a hotel desk, okay? And you're ringing it, like ding, 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 ding. I want you to imagine that. That noise should happen every single time you see limit as h approaches 0. Because we are not going to treat these like regular limit problems. Does anybody remember what these really are? It's the definition of derivative formula. So I want you to look on your Ultimate Study Guide. Okay, and I want you to look at the front. It's hard to tell which is the front and the back, but I want you to find where it says derivatives in the middle column right here. And we are going to be filling this out each day. You are welcome to write anything you want on this. I'm just going to give you suggestions. Okay, the derivative of f of x, which we know we could also write as f prime of x. By definition, that is the limit as h approaches 0, ding, 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 annoying dings, okay, of f of x plus h minus f of x all over h. They could put h in any problem they wanted to, but typically it just gets put in this type of problem. So when you see limit as h approaches 0, what they're really asking you to do is to take derivative of that function right there. All right, so if we move back over to the mini mock exam real quick. If you notice, limit as h approaches 0, that dinging is going off in our head. This is definition of the derivative. The function is sine x, and the derivative of that is cosine x. This is about as easy as any of these problems get. What to do is really not that hard. Knowing that you had to do it, that's the hard part, but once we study this enough, it won't really be that hard at all. So I want you to look on your packet 1. Okay, yours actually says packet 1 right up here. In this packet, if you look kind of at the title here, limits, continuity, and differentiability. That's what we're going to review today and tomorrow. Do you see any problems that have limit as h approaches 0?
5.
5 and even 3. Now 3 is a little bit weirder because, do you see how it should say x plus h and x? Okay, what you're going to do is you're going to imagine that's an x, and then you're going to plug in 1/2 after you derive. Okay? Those are ones you're going to do on your own in a little bit. Number 5, this is also limit as h approaches 0. You have to identify the function and take the derivative. Okay, and you're going to have some class time to work on that. All right, let's look back at the mini mock exam. So we're going to be switching between the 3 things. And if I can do it up here, you can do it with the papers in front of you. Okay, so look at problem 2. This is a limit. There's no h. Okay, so this is not definition of the derivative, but it is a unique type of limit because it says as h, or sorry, not h, x approaches infinity. When you see limit as x approaches infinity, that is a horizontal asymptote. Okay? Another phrase we use for this is called end behavior. Think about when x is really, really, really big. Okay? We're talking about way over here to the extreme right. We're saying, what is the y value? That's why I only care about the largest exponent. Okay, and if you remember about your horizontal asymptotes, we had that nice little rhyme. Which part of the rhyme does this follow? Yeah, degrees. The degree is the highest exponent. That's why I've crossed off the other stuff. Degrees are the same. Play the coefficient game. So 2 divided by -1, that's -2. There's nothing on your green sheet for this because I find students tend to remember this pretty well. But if you're like, I don't remember it that well, then you may want to put something on your green sheet. Like, here's just a suggestion. Maybe like right here by the word limit, maybe give yourself a reminder. Limits as x approaches infinity. Those are the same as our horizontal asymptotes. Okay, so back to the mini mock exam. What if this problem had said 2x to the 7th and the degree on top was bigger? How would that change my answer? However low, slant you go. So what does that mean for the limit? Okay, think about what a slant asymptote does. It would look like this. So as x gets bigger, what would y do? Get bigger, really big, like infinity big. So which of the answer choices then would you pick? Does not exist because infinity is kind of like a D and E situation. All right, what about if the bottom degree was bigger? 0, which is not an answer choice here because that wasn't what they asked you. Okay, so moving on to problem 3. All right. Which of the following is true about this function? Now, look at your paper, look at mine. Did you factor the denominator? Because when you're talking about asymptotes and continuity, factoring is your friend here. You want to factor because if something cancels top and bottom, what does that mean you have? Bless you. You have a hole. Does anybody remember the technical term for that? Which type of discontinuity? I'll tell you, there's 2 options, removable and non-removable. Removable, because it cancels out, right? You remove the hole when you do the problem. A vertical asymptote is called a non-removable discontinuity. So both of these are discontinuous. Okay, so we know Roman numeral 1 is not true. 2 says vertical asymptote at x equals -3. We get that by just setting the denominator equal to 0. And then 3 has to do with horizontal asymptotes, which we just reviewed. Okay, so 2 is the only true one. All right, we're done with the mini mock exam for now. So we'll kind of put that away. And what I would like for you to do is to look back at your green sheet and let's review a little bit more about limits. Okay, so let's see how much of this we can fill out. So limits from the left of f of x is x approaches a. Does anybody remember how we write that? Yeah? Okay, but how do we say from the left? What do we put right here? We put a little minus right there. And then from the right, that would be a little plus. And so this type of notation we use sometimes with piecewise functions. Sometimes we use this with graphs. Okay? If the left-sided limit and the right-sided limit are different, then what does that tell us about the limit?
They're not. It does not exist.
We get that the not continuous, and y'all are a little bit ahead of me, but even more basic, then the limit doesn't exist. Okay, so situations where the limit fails to exist, the most basic one would be where the left-sided limit is not equal to the right-sided limit. This would be like the situation I told you about at the beginning of the year. Like, we're going to meet for lunch, and we're like, cool, we're going to meet at Qdoba. You go to the Qdoba in Richardson, and I go to the Qdoba in Dallas. We didn't meet, if that happens. Okay? So, that's the most obvious one. What that would look like on a graph is something like this. You'd have something like that, but then, and this is called a jump discontinuity. You don't have to know that, but just to kind of put a name to that. All right, what about another time the limit fails to exist? Okay, so thinking about this algebraically, if we get 0 in the denominator, we plug in the numbers for the limit and we get 5/0. What graphically causes that to happen? And we just kind of saw it in that problem we were looking at. A vertical asymptote. So that's the other situation. If you have a vertical asymptote, you can never meet. You can never meet. Okay, we just keep, even if we were both going up on the same side, or the two sides were going up, we'd still never meet. Does anybody remember the third situation? This one's really weird. I'm going to give you a hint. It looks like this. He goes, woo. Do you remember what that's called?
What's it start with?
It starts with wild.
Will.
Wildly oscillating. Now, this one is not very popular. It hardly ever happens. And it almost always happens with a picture. So I'm just putting it in there, okay? Okay, so we're going to practice this whole left-sided, right-sided limit thing in a little bit. Let's go ahead now, before we get to that L'Hopital's rule blank, and let's look at the packet, and I would like to do problem number 4. I believe it's 4. Yeah. I like this problem. So let's go over what we already reviewed. Is the bell ringing in your head?
No.
No, why not? What's not there? H approaches 0. Not there. So this is not definition of derivative. Is it infinity? Nope. So we're not using horizontal asymptotes. Those are the special situations that you want to kind of see first. If it's not those, then all you really got to do is just plug the number in. Okay, so we're going to plug pi over 4 in. All right, so we're going to do, oops, sorry, I didn't mean to write limit. Okay, so we're going to do sine, instead of x, we're going to put pi over 4 in there. The other reason I like this problem is because it has some trig. Pretty basic trig, though. So you just plug what it says x is approaching, you just plug that in for x. pi over 4 minus pi over 4 is obviously 0. So what is sine of 0? 0. You need to know that. The bottom is also 0. So does anybody remember what we do for 0 over 0? Okay, so I heard a few different things. So we do more. This is called indeterminate form. All right, infinity over infinity, same situation. So when this says do more, that could mean factoring. Do you think that's what we can do here, though? No, factoring doesn't make any sense here. So, does anybody remember something else we could do? What does LHR stand for? L'Hopital's rule. Okay, so L'Hopital's rule was a nice little rule that said when you get 0 over 0 or infinity over infinity, you can do the limit, but change up what you're taking the limit of, and you should still get the same answer. So we take the derivative of the top. So derivative of sine, cosine, we're going to now apply chain rule to this derivative. So we're going to keep the inside the same, and we would be thorough here and multiply by the derivative of the inside, 1. All right, so derivative of the bottom, what's derivative of the bottom? 1. Okay, and then we just plug the number in again. Some people forget that part. They take the derivative and they're like, now what? Well, now you plug pi over 4 back in for x again. Now, it is possible that you could still get 0 over 0, in which case you would apply L'Hopital's rule again and again and again until it works. I haven't seen it happen like over and over again, but it could in theory. All right, what is cosine of 0? 1. You need to know that. So the answer is 1.
You could get a 0 as an answer.
We could have gotten 0 as the answer, correct. If it's 0 over 0, you would do L'Hopital's rule again. But if it's 0 over 1, then the answer is 0. Okay, if it's a number that's something other than 0, like 4 over 0, that's when you would pick non-existent.
So for L'Hopital's rule, just take the top and off.
Yep, so let's sum up L'Hopital's rule right here in this box. If you are doing the limit as x approaches a, and I'm just going to write f of x over g of x, if you're doing that, and you get 0 over 0, and in parentheses, I'm going to go ahead and write infinity over infinity, because it's the same situation. This is not as likely to happen, because we have horizontal asymptote rules for that. But if that happens, then you're just going to do the same limit, but with f prime over g prime. Am I doing quotient rule here? I'll answer that. No, I'm not doing quotient rule. Okay, quotient rule is more complicated than that. We'll review that on Friday. Okay, so that's L'Hopital's rule. It comes in handy. It's because if we didn't know L'Hopital's rule, you would have to kind of memorize some other things about limits more than I've had you memorize. But with L'Hopital's rule, it solves that. We really can do a whole lot of problems with that. All right, look at your packet really quick. And on that very first page, does anybody see another problem that looks like it could be solved with L'Hopital's rule? And it's on the first page. Here's your hint. Okay, why is that a L'Hopital's rule problem? Yeah, when you plug 0 in for x, you're going to get f of 0 over g of 0, which they tell us right here are both 0. So you have to apply L'Hopital's rule, and that's what this stuff in here is for. And you're going to do that one in a little bit. I just wanted to give you a heads up here. All right, let's talk about continuity now. Oops, there we go. I really should make this bigger. I'm going to do that. Should have thought of that earlier. Okay, continuity. Okay, so let's talk about how continuity is related to limits. So I want everybody to put your hands up like mine. This is for the audience participation part of the lesson. Okay, and if we want a limit, what has to happen to these two hands? They have to meet. Okay. If there's a hole there, we can still have a limit, but what would not happen in that case? And your hint is right up there on the board. It would not be continuous. Okay, so we have a couple of things happening here. Okay, in order for something to be continuous, the first thing that has to happen is we have to have a limit. The second thing is they have to meet an actual point. Okay, not a hole. So, and I'm kind of explaining this again in different ways than I taught it, so that I want you guys to make connections. You can't just memorize all this stuff independent of each other. So the first thing for a function to be continuous is the limit has to exist. And this probably will imply that the left and right-sided limit are the same. Okay, and we're going to... This is the 3 rules, and we're going to practice this here in just a second after we write these down. All right, so I said the limit has to exist, which means they have to, the two sides of the graph have to come together right there, and they cannot come together at a hole. The limit part would be okay, but the continuity part would be messed up if there was a hole there. So there has to be a point that they meet at. Algebraically, we write this as f of a. F of a has to exist. And that would be the point, if you want to write that in parentheses. Anybody remember the third thing? It kind of wraps it all together. Yeah, these two things have to equal each other. This was that thing I put on like all your quizzes and tests for a long time into the first semester. But we really haven't talked about it a whole lot since then. So it should sound familiar, but we need to practice it. So let's look at the packet. I want you to turn all the way to 24. This is a free response. You guys remember how much free response is worth? 9 points, right? And 9 points, and this is only parts A and C because those are the only parts that apply to this topic. And so I'm thinking that part A was probably worth 2 points and part C was probably worth 3 points. And we're going to work both of those right now. So we need to do 3 things. This is not a lot of room. Okay, so I'm going to start up here. On the actual AP test, you will get like literally a half a sheet to do every single part. So like 2 full pages for a whole free response. So a lot of room. I know there's not a lot of room on this packet. That's okay. You can use notebook paper if you want. Okay, so if we want to show that f of x is continuous at x equals 3, the first thing I have to do is show that the limit exists. Now this is a piecewise function, so we're going to do the left-sided limit and the right-sided limit. So in a piecewise, one piece is going to be the left and one's going to be the right. Look at the inequality symbols to know. The left piece is going to come from where x is less than 3. And so I'm going to write that right there. And then I'm just going to plug 3 in for x. And that simplifies to 2. Okay. Now we need to do the right-sided. So we pick the other piece, the 5 minus x. That's because that's where x is greater than 3. And we get 2. Honestly, it would have been better if we hadn't gotten 2, because then I could just say limit doesn't exist, not continuous. Because these are the same, I need to say something about the fact that the limit as x approaches 3 exists. And I'm going to go ahead and say that it equals 2. You don't have to write both of these things. You could write equals 2 or you could write exists. Both, either one would be fine. You don't have to write both. I'm writing both more for your benefit. Okay. So that was all part 1, although that's the hardest part. Okay, do you remember what we have to show in the second part? The point. So we need to know what f of 3 is. Now, intuitively, you probably already know what it is from doing the work up here. You look at the or equal to part, and then you plug that in. Now, we already know what happens, but we'll just write it down. Okay, and again, you don't have to write exists. I'm doing that more for you. Don't forget, though, you have to wrap it up, which means you have to show that these two, that you know that these two are the same. So the limit as x approaches 3 of f of x, that has to equal f of 3. And once we've shown that both of these things exist, they both equal 2, we can say, therefore, f is continuous at x equals 3. Do y'all remember this a little bit now? I mean, we need to review this stuff. We don't remember all of it, but does it sound familiar? Or are there any questions about it now?
We abbreviate.
I wouldn't abbreviate much more than I am.
Yeah, but like, people like, they don't get.
Yes, this is an acceptable abbreviation. If you're ever not sure on the actual test, just write it out. It's not going to hurt you. If it comes down to that.
So if we don't put all 3 of those.
So I will tell you that no matter who your grader is, what year they grade or who it is, I know this would get you full credit. If you do anything less than this, it's possible that year there's certain things that they didn't require. I can't say, I don't know. So
Just do it all.
that's a safe bet. Just make sure you have all that.
How do you know? What happens like the third condition? Like, how did the condition?
So in a piecewise function, the third condition wouldn't be met if, say, there was like a third piece. Like, see this or equal to here? Let's say that wasn't there, and there was a third piece that said for x equals 3, and it was a whole different number than 2. Now, that's probably not likely to happen on a piecewise function, but it definitely could happen on a graph. Like, if the graph looked like this. Conditions 1 and 2 are met, but 3 is not met. Okay. All right, so let's look then at part C. You can tell they kind of changed up the piecewise function. They gave it a new name. And they say K and M are constants. That means numbers, so keep that in mind as we look for them. And it says G is differentiable. So let's think about, what does differentiable mean? That we can take the derivative. Okay, so if G is differentiable, that is going to imply that G is continuous. If you think about this logically, it should make sense, because if you can take a derivative, you can only do that if there's actual points there. If there's a hole or a vertical asymptote, you can't take the slope of that. So, and there's some other things that have to be true. Okay, so I'm going to come back to this, but what I would like to do is go ahead and fill this part out on our study guide. So it's kind of like up here. I know it seems like we're jumping around a whole bunch, but really this is just to it's to kind of go in a natural order of kind of how we review it. Okay, and if there's other stuff here that you remember, feel free to fill that in today. You don't have to wait till I show it. Okay, situations where derivatives fail to exist. Okay, if a graph is not continuous, then there's no derivative. Okay, so if there is a derivative, then I know that the graph has to be continuous. Does anybody remember another situation where there's no derivative? A cusp. Okay, do you know why that is the case?
Different. Because it's at 0.
Okay, look at what's happening right there at that cusp. The slope doesn't change gradually. Look at the slope. It's one thing, and then drastically in a split second, it changes to something else. Okay, so that's not differentiable. And then there was one other one. What type of line is not, the slope does not exist? A vertical line, we could say, has no slope or a undefined slope. Okay, so if you have a graph that is vertical, even just for a split second, that is not differentiable. We call this a vertical tangent. Again, this is kind of less common. So let me show you what this means. It would look like this, where a graph goes vertical for a split second. This could be like cubed root of x. Okay, so those are the situations where a derivative fails to exist. So what we need to do now is kind of apply that to then answer the question, and this is the last one we're going to work together, okay? So we're going to kind of look at two different things. All right, and I'm going to even put them in different colors just to kind of point it out. Okay, let's just deal with continuity. If this piecewise function is continuity, then the two pieces should meet like that. Meaning the two pieces should equal each other when x equals 3. So watch what I'm going to do. I'm going to set the top piece, and again, I'm plugging 3 in for x. I'm going to set that equal to the bottom piece, and remember, x is supposed to be 3. We only care about when x is 3. That's why I'm only doing that part, or that's why I'm plugging that in. We are going to have to do a little bit of algebra. What I'm going to suggest first, though, is let's just simplify this a little bit. We have to solve for k and m, so we got to use some algebra here to get k and m by themselves. So let's first just clean it up a little bit. We know that square root of 3 plus 1 is 2. We did that earlier. And then m times 3, I'm just going to write that as 3m. Now, if there was only one letter here, I could solve for that pretty easily. It does. But that wouldn't make sense, would it? This is an M. All right. Okay, so there must be something else in this problem because I don't have enough information to solve for k and m. This is where we come over here. All right. You can take a derivative of a piecewise function. Let's go ahead and do that here in this. We're going to practice finding derivatives a lot more in a couple of days, but we can do this one for now. Remember, k is a number, so let's just write it and write the time sign. How do you derive square roots? Here's your hint. Okay, bring that 1/2 down, keep the inside the same. The new power should be -1, so -1/2, and then you should always go times the derivative of the inside. In this case, that's a 1, wasn't a big deal. Okay, the bottom piece is actually much easier to derive. Remember, m is a number, so like think of m as like 5. What would the derivative of 5x plus 2 be? 5x. 5, right? So mx plus 2 would have a derivative of m. Does that make sense? If that had not had an x next to it, we would have said 0 here. Okay, so we're going to do the same thing with this. We're going to set these two things equal to each other because if this is differentiable, the derivatives should be the same. Again, at x equals 3. That's a key. So make sure you plug 3 in for x. I'm going to drop the times 1. So I said earlier, there's like 3 points allotted to this problem. You get 1 point for setting up the first equation. That one, none of this is easy, but that was the easiest point to get here. The second point you get from setting up this equation, and the third point is for solving for k and m, both of them correctly, okay? So you really got to work for that third point. Now, the rest of this is algebra, and when you get to college, when your professor says that, that means they're moving on to the next problem. We're not there yet. I get that the algebra sometimes is the hardest part of the problem. So I want to explain this. 3 plus 1 is 4. Okay, the negative in the power means 1 over, and the half means a square root. So that turns into 1 over square root of 4. Okay, which is 1/2. I'm not going to skip many steps here because I want to make sure you guys follow this. 1/2 times 1/2, that's 1/4. And I would love it if I did not have to deal with fractions. So what's something easy I could do to get rid of the fraction? Multiply by 4. So I end up getting k equals 4m. So I still don't know what k and m are, but I'm a lot closer because I could use what I know about algebra and I could plug that 4m in for k. I'm basically solving a system of equations. Okay, like I said, we're working hard for this third point here. Once you do that substitution, then you only have a single letter and it gets much easier. So 2 times 4m, that's 8m. 3m plus 2. At this point, you shouldn't have to look up at the board. If you've already copied this far, you should be able to finish this problem on your own. Go ahead and solve for m, and then use that information to solve for k. You need both of them. Okay, what did you guys get for m? 2/5. Okay, k, you're fine to just write 4 times 2/5. Remember, you don't have to simplify on the free response. Okay, some of you right now, I'm a mind reader, and I know you're thinking, I never would have thought to do that. And that's okay. The goal is not here to get 100% of the points. Okay, the goal is, it's different for everybody, but there are going to be some points that you don't get. That's okay. All right, I'm reviewing this because for some of you this is an easier problem. For some of you this is going to be the harder problem. Okay, so you don't need to get anxiety over I wouldn't have thought about this. I think a lot of you though could have gotten the first point if you had just walked it through and not freaked out. Okay, it's a mental game more than anything else, I think. All right.